Okay, good afternoon. We start the semester off with pretty straightforward financial mathematics piece. Excuse me, that we eventually build up later on into something bigger. So the motivation for this is to sort of get a handhold on how these formulas work, and then make them a little more complex next week and the following week. And so hopefully you've all probably seen this before, or at least heard of it. And our topic is first and foremost compound interest, which comes from investing. Right? So it's this idea that you invest a sum of money at a certain annual percentage rate. You have compounding periods, and you compute over time how much money your money makes while it's sitting in a bank or some kind of mutual fund or something like that. And like I said, this is really a lead into something much more complex. So for now, this is basically a warm-up, and it gives us a chance to do some work with some exponents and get some math in there as well. So let's just start off with a little example here, which will help us get to the theoretical piece. If we invest $1,000 at 4% annual percentage rate for 3 years, how much money do we accumulate with monthly compounding periods? Actually, the better way to do this would be, let's start off by saying, where's that thing? Annual compound. So let's say we only compound once a year, which no one would put up with, but it helps us get a handle on this formula. So you start off with some deposit, which we'll call the principal amount. And that's P. That's $1,000. I already lost my voice this week. And our interest rate is 4%, which is an annual interest rate. And we use T for time, and T is measured in years. Okay. For now, we're compounding once a year. So our accumulation is what? We start off with, I'll call this A0. So at time zero, we got $1,000 in the bank that we're putting in. A year passes. So at the end of year one, we have that $1,000 plus our interest payment, which is 1,000, so 4% of 1,000. And that becomes 1,000 plus 40, which gives us 1040. So at the end of year one, we have $1,040. But let me put this in white. If you look at this first line here, it's, if you factor out the 1,000, this is 1 plus 0.04, which is the principal times 1 plus the rate. Okay. All right, so now we go to year two. So in year two, we take the money we had at the end of year one, which is $1,040, added to the interest, which is 1,040 times 0.04. And you get what? Factor out the 1,040, and this is 1 plus 0.04. And so this is what? 1,040 times 1 plus the rate. But 1,040 we already computed to be this guy. So we have put that in white here. I'm trying to get my colors straight. P times 1 plus R, that's the 1040, times another 1 plus R. So I have P times 1 plus R squared. And if you continue in this manner, on the kth year, you have what? You have P times 1 plus R to the K. Okay. And in this case, K is just going to be whatever the number of years is. So we have P times 1 plus number of years T. All right, so this is for, if you did this for 3 years, you'd get, I don't know, $1,200 or something. Now let's extend this to compounding periods that are not once a year. Okay. But basically what you do is you just do this. So if we compounded monthly, so 12 times a year, the rate has to be divided by 12. So we have our principal times 1 plus the rate, and the rate's going to be divided by number of times per year, which is in this case 12. And then the number of compounding periods is going to be how many times we multiply 12 times the number of years, right? So basically we have 1 plus R, I'm going to use M times to the mt power. Okay, so P is principal amounts. R is annual percentage rate. M is number of compounding periods per year. And T is number of years. Okay. And this is an important formula that again comes back when we talk about annuities and stocks, and it just gets adjusted and tweaked. So just to have a solid exercise here, let's compute the accumulated amount of the above example with monthly and daily compound periods. Right, so if we were doing it monthly, we would have 1,000, 1 plus 0.04 over 12 times 12 times 3. So this is 1,000 times 1 plus 0.04 over 12 to the 36. So that would be for monthly, and you plug that into a calculator and get some number. I don't know what it is. And if we were doing it daily, this would be 0.04 over 365. And then up here we'd have 365 times 3, and this would give us some amount. And if you wanted to do it every minute, you would, take 365, or so every hour, 365 times 24. You would have this. So 365 times 24, and then up here it would be 365 times 24 times 3, and you get some number. And what you'll notice is that these numbers don't change much. Okay. So what's happening here is that no matter how many compounding periods you have, at some point, the amount you get back levels out. And that's because of, it's because of nature. to be very obtuse. Okay. So let's look at what's going on here with this formula. So we have this guy, 1 plus r over m to the mt. Okay. Now, if you think about it, if we want to examine here, let's examine how this number changes as m increases, as we increase the number of compounding periods per year. Okay. So in that case, like we just had, let's fix P, so some set amounts put in there, so it's a number. Fix R, that's just given, it's an interest rate, that doesn't change. And let's fix the number of years, it's just T, it could be 1 or 5, or just fix it. So what happens is, A, this accumulated amount becomes a function of M only. Everything else, even though they're letters, are fixed. Okay? So the only thing moving here, the only thing varying is M. So using this function notation, you see here that the only input that's moving is number of compounding periods. All right, so we're gonna do a little trick here. This is a math trick. So we're gonna let U be M over R, and then plug it into this. So we have P, and if U is M over R, R over M is 1 over U, and M is RU, so we have URT up there. So I just did a change of variable in there. And A is now a function of U only, and U is a function of M, so it's embedded in there. So as M grows, U grows, and so does A. All right, we're going to rewrite this. I'm going to read that like this. So this is 1 plus 1 over U to the U. And then I'm going to take this RT and put it outside here. Remember, RT is a fixed number, so it's just 5 or something. Okay. Now, this is going to show up a lot in this course. This idea of this number here, 1 plus 1 over U to the U. So if we have, so now let's examine this number 1 plus 1 over U raised to the U. As M gets really big, as it goes to infinity, U goes to infinity, because M gets big and U gets big linearly together. This number, it converges to roughly 2.73. It's actually the number E, the natural number E. So if there was such a thing, if we could compound interest continuously, meaning every second, or every microsecond of every morning of every day, night, you were compounding continuously, then the accumulated amount would be PE to the RT. And some of you may have seen this. I always joke about it when I taught high school as PERT, the shampoo or whatever. But that's because this inner term here, this whole thing up here, really becomes E. Okay? Now, the story I learned in college was that there was a bank in the 30s that advertised continuously compounding interest, and that there were lines around the block for people taking out their money from other banks before they figured out that it's not much different than if you compound monthly, especially if you're putting in small amounts. If you're putting in $1 trillion, yeah, any change is going to make a lot of money, but you know, not many people have that kind of money. Okay. All right, so we have that now. PERT. And I'll assign a couple of homework problems where you have to find compound interest for different setups. So when I was younger, and I actually put money in the bank back when savings account had real, I think I got 4 or 5% when I was a kid on my little $200 investment. I could never figure out what the difference between APR and APY. I always knew the APY was higher, and I vaguely remember thinking, oh, can I choose the higher rate? Meaning I thought it was a choice. Like you could invest at 4% and it would be like 4.75 APY. I was like, well, can I have the 4.75? So APY stands for what? Annual percentage yield. And your book uses the term effective rate of interest. So no book is perfect. I would prefer to use APY because that's what I've seen since I was 14. But that's what your book is using, and so there we are. And little r, the annual percentage rate, they use nominal. It could be that nominal and effective interest rate, those terms are for professionals, whereas APY and APR are for us mere mortals, so who knows. And APY is the actual percentage you get at the end of the year, and that changes with the number of compounding periods. Okay, so the idea is this. So we're gonna let capital RP be this APY, this effective R sub F, this effective rate of interest or annual percentage yield, and we're gonna let T be 1, just what happens in 1 year, because that's what APY means. It's after a year of this work, and after a year, your principal is going to be what? It's going to be the principal times 1 plus this rate, right? Which we don't know. So we want to solve for R somehow. I want to figure out what this R is given number of compounding periods in little r. Okay, so we take this P times 1 plus cap R and we set it equal to our formula. Okay. And remind yourself that T is actually 1. So what I have is P times 1 plus R over M to the M. Okay, so first of all, across here we divide by P. It's non-zero, so that's a legal move. Oops. So on the left-hand side I have 1 plus R, and on the right-hand side I have 1 plus R over M to the M. And so cap R we solve for is 1 plus R over M to the M minus 1. And that's how you compute APY with this formula. All right. So going back to this formula, which is really what today's whole talk is about. how can we solve for all of these different variables? So that basically means different questions here. The most basic question is I give you a P, an R, an M, and a T, solve for A. All right, plug and chug. But what are some of the other questions you could ask? Like the big question is how much to invest so that after a certain amount of time, I have a certain amount of accumulated money. So here, let me make this formal here. How much should I invest to accumulate some set amount over time? Right, so let's say you're retiring in 5 years, so that's your T, and you want to put how much money in now so that in 5 years you have $50,000 or something like that. Right? Or how much should you invest at 6% interest? That's a really good interest rate. Compounded monthly, so that in 3 years you have $20,000. So to do that, we need to solve for P. So solve for P. In the above equation. Okay. So here's some fun math here. We have, let me put it out here in the center. A equals P times 1 plus R over M to the MT. So if I want to isolate the P, you can divide by 1 plus R over M to the MT, or multiply by, this is the better way to do it, multiply by 1 plus R over M to the minus MT, right? And anything I do on one side of the equation, to the other side of the equation. So when you solve for P, you take the amount you want and you multiply it by 1 plus R over M to the minus MT. Okay, so what do we want? We want $20,000 at the end of 3 years. Our rate is 6%. Our compounding monthly, and it's minus 12 times 3. So that's 20,000, 1 plus 0.6 over 12 to the negative 36. And when you plug this into a calculator, you get $16,712.89. So if you invest that much now at the 6%, in 3 years, you'll make it to your 20,000. Okay, so that's that. So again, coming back to this, today's sort of thing here. What if you wanted your money to grow from 10 to 18,000 in 5 years? What rate would you need? So the next question is here. These are rate questions. Rate questions, right? Solving for R, and this is the hardest of the group here. And this is really going to be maybe something you've never seen before, but something we'll use a lot in this course, again, mathematically, to get at it. So here we are, another example. We want to find the interest rate needed for an investment of $10,000 to grow to $18,000 in 5 years, and assume monthly compounding. Okay. So basically we're solving for R. Okay, so let's plug everything into this. So the accumulated amount is going to be 18,000. The principal amount is 10,000. We don't know what R is, that's our variable. We know what our compounding period is 12, and then up top here we have 12 times 5, which is 60. So we want to solve for R here. So the first thing we're going to do is do some dividing here. So these zeros cancel. And what's 18 over 10? It is 9/5. So I have 9/5 equals 1 plus R over 12 to the 60. Okay, so how do we get that 60 to come out from the exponent there? It's no small feat, and for that we need logarithms. I'll almost exclusively use natural log, which is ln. So we take the ln of both sides. So I have the ln of 9/5 equals the ln of 1 plus R over 12 to the 60. Okay. Okay, and so now we use some rules of logarithms here, which you may have forgotten. One of which says that when you have the ln of an argument, my pen is, to a power, the power comes out front. So this guy can shoot all the way out front here. So this right-hand side becomes 60 times the ln of 1 plus R over 12. And that equals the ln of 9/5 on the left here, okay? And so we're getting closer. Now we can divide both sides by 60. And your calculator is going to have an ln button on it. So you take the ln of 9/5, divide it by 60, and you get something like 0.009796. And this equals the ln of 1 plus R over 12. Okay. Again, let's not lose sight of what we're doing here. We're solving for R. Okay, well, the undoing of an ln involves the natural function, the natural number e. So this is another famous trick because we're trying to get rid of the ln. So now we're going to raise the left-hand side. So there's going to be e raised to this number equals e raised to the ln of this number. Okay. And so on the right-hand side here, so e to the ln of a equals a. This is a fact for any a. So e to the ln of 1 plus r to the 12 is 1 plus r to the 12. 1 plus r over 12. So now I have e to the 0.009796 equals 1 plus r over 12. We're getting closer and closer, right? That r is about to be all by itself and we'll have the problem done. Okay. And so subtracting 1 from both sides and rearranging here, so I have now r over 12 equals e to the 0.009796 minus 1. And finally solve for r by multiplying both sides of the equation by 12, and I have e to the 0.009796 minus 1. And this is a calculator thing. You plug this whole thing into your calculator and you get 0.1181, which is 11.81%. That's the r. Okay, so basically what we've done here, to conclude, the formula for compounding interest, very simple, is this. And now we can solve for any variable. And the big thing with these kinds of courses is how do you transform the language of a problem, because it's all language, into the mathematics. And for these investments, it always has something to do with this formula and how you set it up and what you solve for. So. All right, I apologize if the sound wasn't very good. I have a really nice external microphone that I brought home to make these videos with and forgot the cable. So it's sitting here next to me, but I can't connect it to the computer. So there you go. I'll see you in class in a few minutes.